Okay, welcome to class for Wednesday, April 15th. Today we are going to talk about rotation. We're going to start off on our we'll spend the next week and almost 2 weeks really talking about rotation. We've talked about it a little bit already, but we'll get into it a little more. So announcements. This week is Wiley Plus catch-up week. So please catch up on everything that was due previously on Wiley Plus. On the adaptive practice, what I've decided to do, and I'll send this out in an email, I'm going to, it gives you scores in increments of 2.5 points. I have no idea why 2.5 points, but for some reason it'll give you a 0, a 2.5, a 5, a 7.5, or 10 on the adaptive practice. I'm going to cap those scores at 5 points. So if you got 7.5, wonderful for you. Basically, what that means is you need to get full credit, you need to get 5 points. If you get 2.5 points, you get half credit. Yeah, that's about as fair as I can make it. So if you have, 5 points or more, you can just stop on the adaptive practice. Unfortunately, I don't believe it will tell you what your grade is on the adaptive practice until it's due. But remember, I'll keep pushing the due dates back so you can get some feeling for that. Mostly for the adaptive practice, I want them to take the position of the clicker questions. I want them to give you a chance to sort of try it out and work through it a little bit on your own. Get the brain muscles working a little bit. The next perusal reading assignment is next Wednesday. That will be on torque. And video experiment number 6 is up tomorrow. Finally, the final exam. So the final exam for this class is going to be an oral exam. I will email out after class a link to a doodle poll where you will need to sign up for one of the time slots available during finals week. I know many of you don't have your final schedules yet. The campus hasn't released them. So if you want to hold off on signing up for one of these things, that's fine. If you just want to pick one and sign up for it, and then we can move it around if you need to, that's fine too. But I have no idea when campus, the official, like the student portal is going to show your finals. Normally that happens about the beginning of April. For some reason, it hasn't happened yet, and I can't get anybody to tell me why. So we'll find out. Okay, questions about any of that stuff? All right, let's start off with actual physics. So you are looking straight at a clock on the wall. Which hand has greater angular velocity, the minute hand, the hour hand, or they both have the same angular velocity? All right, I'll give you another 10 seconds or so. All right, going once, going twice. Sold. Okay, almost everybody said the minute hand. Almost everybody's right. The minute hand has greater angular velocity. All right, here's the follow-up question. Let me relaunch the poll. Okay, can you see it?
Yes.
Great. It seems to be about 50-50 whether or not that actually pops back up again. Okay, so now you're same thing. You're looking straight at a clock on the wall. In which direction is the angular velocity of the minute hand on a clock at exactly noon? All right, I'll give you another 10 seconds on this one. Going once, going twice. Sold. All right, now this one's interesting. So I'll share the results here. Almost everyone said B to the right. So if it's a minute hand at noon, which way is the velocity of the minute hand? And that's what you're saying, to the right. The velocity is to the right. Now, but the question wasn't which way is the velocity. The question is which way is the angular velocity. And for that, we're going to need a trick. So this is called the right-hand rule. It would work if we did all of physics and engineering left-handed. That would work too. But we did it right-handed. Sorry, lefties, because righties are just sort of jerks like that. So if you have something moving in a circle, right? You have a nice circular motion, okay? The direction of the angular velocity is, if you take your right hand and you curl it in the direction of motion, right, in the direction of rotation, your thumb points in the direction of the angular velocity. So for a clock, the minute hand's angular velocity is actually pointed, if you think about a clock on the wall, right, and you turn your fingers in the direction of the hands of the clock, the answer is actually C, into the clock, okay? Now, this seems a little bit wacky, but we'll explain why here in just a minute, okay? So just to restate here, when we're talking about velocity, the velocity of the minute hand of a clock changes, the direction of the velocity changes as it goes around an hour, right? But the angular velocity never does. The angular velocity of the minute hand of a clock or the hour hand of a clock is always pointed in the same direction, okay? Which gets at why we want to talk about rotation. So let me stop sharing my screen and come over here and talk to you just for a minute. So when we talk about rotation, we need to talk about the other kind of vector multiplication. If you remember way back when we learned about vectors, we learned that there are two types of vector multiplication, right? The first one we saw when we got to work, right? The work of a constant force is just the force dotted into the distance vector, right? This is a dot product. A dot product takes two vectors and makes a scalar, okay? So work doesn't have a direction attached to it. The other type of vector multiplication is the one we're going to have to think about today, which is that if we have two vectors, so let me draw some. Here's vector A, Here's vector B. Okay. It turns out we can multiply these two vectors together in such a way to get another vector. And we call that the cross products. So we'll say vector C is A cross B. Okay. So this is a dot product. A dot product takes two vectors and gives you back a scalar. This is a cross product. The cross product takes two vectors and gives you back a vector. So how does it do that? Well, there are several ways to do a cross product. Okay. The first way to do a cross product is to think about these two vectors, right? And just do it with your hand. So the way you do a cross product involves your right hand again. Do it right with your right hand. Don't do it with your left. I once accidentally, I was taking a test for the equivalent of 204B class. You'll do lots of cross products in 204B. And I was writing with my right hand, so I accidentally used my left hand, which meant every single one of my answers was wrong by a negative sign. And I'll show you that here in just a minute. But the general way to do a cross product, to figure out direction, take your right hand, put your fingers in the direction of the first vector, A, and curl them towards the second vector, B, and your thumb will point in the direction of vector C. Okay? Now, I wish we were in a classroom because this is hard to do on a camera. So what I want you to try to do is actually try this for yourself. Draw two vectors on a page. So A, put your fingers in the direction of A, curl them towards B. C is where your thumb is pointing. So in this case, the vector C is pointing into the page. Okay? And we can denote that like this. This is supposed to be like the tail of an arrow, I guess, but this means into the page, okay? So if C is the cross product of A and B, it is into the page, okay? Now, you may have noticed that if I did the cross product if I did B cross A, I'm going to get something different. Let's call that one D. So if I put my fingers in the direction of B and I curl them towards A, now the cross product is pointed up. My thumb is pointed up. So vector D is going to be out of the page. A circle with a dot in it means a vector pointed out of the page. Again, this is supposed to be like the tip of an arrow. This is the tail of an arrow. I don't really get the arrow thing, but that's the convention. Okay? So this is the cross products right here. Now, you'll notice that it is not commutative. Okay, if you remember back to algebra, you learned that 3 times 4 is the same as 4 times 3, right? Multiplication is commutative. Vector multiplication is not. The dot product is commutative. The dot product of F and D is the same as the dot product of D and F. But the cross product is not commutative. In fact, if you swap the ordering, you get the negative of your vector. So B cross A is negative C. If A cross B is C, then B cross A is negative C. Okay? So this is a different way to think about it. Cross products are inherently three-dimensional. Okay? Another way to state this is the cross product finds the vector that is perpendicular to both of the other vectors. Okay? That's why both of these vectors are on the page, which means the cross product has to be perpendicular to the plane of the page. It has to be out of the page or into the page. Okay? So let's think about this with the clock, right? Here's our clock. And we had the hand at noon, right? So there's our hand. There's our minute hand. Okay? The velocity vector is pointed this way. Okay, there's our velocity. Our radius vector is pointed this way. Here's our radius vector. Okay? It turns out that our angular velocity vector, let me get this right. Hold on, angular velocity. Okay, so our velocity vector is our radius vector cross our angular velocity vector. Remember, this is omega, right? We talked a little bit about omega. Omega is the angle you're turning through per second. Now, why would we want to do that? Why would we want to talk about the angle something is moving through per second rather than just talking about the distance it's traveling per second? Give me some ideas here.
If you did distance, you would come back to the same spot since you're going in a circle, and it would be kind of confusing.
Right, because if we go all the way around a circle, we're back to the same place we were before, right? But the distance would keep going, right? So the angle gives you an easy way to see that you're repeating something. Okay, that's a good idea. The other thing to think about is that if we think about this minute hand, right? Let's make a couple of spots on this minute hand. Here's one, here's another one, okay? This one is going to go around in this circle. This one's going to go around in that circle. Which one has a bigger velocity?
The bigger circle.
Right, they both go around once an hour, right? So this big one has gone around a lot farther than the little one. So the reason we talk about angular velocity is because every point on this minute hand has the exact same angular velocity. They all have different velocities. And you can think about how this would get really complicated. Because let's suppose I talk about this pen, right? And I spin this pen around, right? Let me spin it this way, right? I spin the pen, okay? Every point on the pen has a different velocity. And if I make a complicated shape like a pen with this little clip here, right? Now that velocity gets even messier. But the whole pen is spinning together, which means when I spin the pen, every point in this pen has the same angular velocity, right? The angular velocity is the same. The velocity is not, but the angular velocity is. Okay? So it turns out that angular velocity is the sensible thing to use when we're talking about the rotation of solid objects. So previously, we talked about an object moving around in a circle, right? Like you remember the water in the bucket. We talked about the object, the water, moving in a circle. Now we're going to talk about what happens if the object itself spins. Like this pen, right? Instead of the pen moving in a circle, this pen is moving in a lot of different circles, right? Because this point on the pen is moving in a little circle, and this point's moving in a big circle, and that point's moving in the biggest circle. So instead of talking about its velocity, we're going to talk about its angular velocity. And along the same lines, you might expect, instead of talking about its position, we're going to talk about its angular position. Okay? Now, you probably never thought of angle as a vector before, but it is. It's a vector. You can spin in 3 different ways. Okay? And instead of talking about acceleration, we're going to talk about angular acceleration. That's the fish thing. Okay? This is a Greek omega, this is a Greek letter theta, and this is a Greek letter alpha. Okay? You may call them curly W, theta, and fish if you want, but really it's omega, theta, and alpha. Omega is the angular version of velocity. Theta is the angular version of position, and alpha is the angular version of acceleration. Okay? So going back to my clock, if I wanted to tell you what this clock is doing, what would its angular acceleration be?
Is it the cross product of R and the fish thing?
Yep. So this is the thing I want. I want this angular acceleration. Okay. If this minute hand's just moving around the circle here, what's its angular acceleration? Well, first of all, if you're moving in a circle, what's your acceleration? Where's your acceleration pointed?
In the direction you're moving, so right, I guess?
The acceleration is? The velocity is?
Yeah.
To move in a circle, which way do you have to accelerate?
That's to accelerate towards the center.
Yes, you have to accelerate towards the center of the circle. Okay? Now, here's the fun part. So that means your acceleration vector over here is pointed right back towards the middle. Okay, now, remember, cross product says I need to find a vector that is perpendicular to both of the other vectors. Now, we're doing this a little bit backwards because the thing we don't know is over here, right? But let's think about this. I need a vector, right, that is perpendicular to R over here, right? Because the result of a cross product has to be perpendicular to both vectors. What's the direction, the difference between A and R?
0.
They're going in this, well, they're opposite directions, right? But they're both going the same direction. So they can't be perpendicular, which means the only answer over here is 0. Okay? In other words, there is no angular acceleration. Okay, let's talk about this a little bit in a little bit easier terms. If, and this is a big if your 2 vectors, so let's say we've got A cross B, and A and B are are perpendicular, then A cross B is just the magnitude of A times the magnitude of B, right? In the direction of the right-hand rule, okay? So if they're perpendicular, the cross product is really easy. you just multiply the two components, right? The two magnitudes. So that means that if they're perpendicular, right? Your velocity magnitude is just r times omega, and your position is just r times theta, and your acceleration is just r times your angular acceleration. Okay? If they're perpendicular. If they're not perpendicular, then we've got to do messier things, which we will get to, but not yet. Okay? So if they're parallel, if A and B are parallel, then A cross B is 0. Okay? So, in other words, as long as you're talking about perpendicular things, you can just do this. Now, here's the other trick to this. When we talk about this velocity, right, going back to our circle, what we're actually talking about is the tangential velocity, right? So if you take a clock and you use it as a frisbee, right? You take a clock and you throw it across the room, the minute hand still has some angular velocity. But I wouldn't use the velocity of the minute hand plus the velocity of the clock as it flies across the room to try to figure out its angular velocity. I would only use the component, the perpendicular component. So what this means here is that we have a whole new set of kinematic variables, right? Instead of position, velocity, and acceleration, we've got angular velocity, and angular acceleration. How do you guess they're related to each other?
Integrals and derivatives.
Integrals and derivatives. So theta is just the integral of omega with respect to time, which is just the double integral of angular acceleration with respect to time again. And the angular acceleration is just the time derivative of angular velocity and the second derivative of angle with respect to time. So this means we can completely redo kinematics for rotating things. So let's think about that. Let's suppose, let's do a sample problem. Where'd my sample problem go? There we go. All right, let me share my screen. Okay. So here's the sample problem I want you guys to think about here for a sec. You have a car's wheels and they're 40 centimeters in radius, and the car is accelerating forward from rest at a constant rate of 4 meters per second squared. What's the angular velocity of the wheels after the car has traveled for 100 seconds? And how many revolutions have the wheels, should be an S there, have the wheels been through? Okay, so how would we do this? So if the car is accelerating from rest at a constant rate of 4 meters per second squared, and it has wheels that are 40 centimeters in radius, what's the angular acceleration of those wheels? Oh, come on. Somebody help me out here.
Would
just
we
talked-
man-
what was
would we
that?
would we manipulate the equations that you gave us earlier
Yeah.
to solve for
So,
alpha?
yes, exactly. So you can take that relationship between acceleration and angular acceleration and use it to figure out what the angular acceleration is. So let me come back over here to my little document camera. Okay. We said that the acceleration is 4 meters per second squared, and the radius is 40 centimeters, which is 0.4 meters. Okay. So if we do this, we know that our acceleration is equal to radius times angular acceleration. So that means our angular acceleration is just our linear acceleration divided by radius, which means our angular acceleration is 10 radians per second squared. Now, why radians? Why not degrees?
Can you
Yeah,
ex-
because
Hold on. Let's answer the question and then we'll go back to Luis's question.
that's because it's the units we use for like circle, right? And it's angular.
Right. Because here's the wonderful thing. What are the units on A?
Meters per second squared.
And the units on R?
Meters.
So that means my units here, right, are meters per second squared divided by meters, which means my units are just 1/2 squared. So I need something that is unitless. And what is a unitless thing? Radians. Every other way, degrees, whatever thing you want to do, right? Those things all have units on them, but radians doesn't. You remember what I talked about? I made the joke like radians are the angles that decent people use. It's not that much of a joke. It's because this is really the fundamental unit for angle is the radian, because the radian works as a unitless number. It's simply because a radian is one radius along the edge of a circle divided by one radius from the center to the edge of the circle. That's 1 radian. So it is a perfectly unitless number. So the angular acceleration here is 10 radians per second squared. Okay, Luis, what was your question?
I was gonna ask if you could explain why did we use that formula of acceleration and not the other one where it's acceleration is equal to r cross alpha?
Okay. So let's talk about this for a second. So if I've got a wheel, okay, the center of the wheel is accelerating forward at 4 meters per second squared, okay? So what that means is that the wheel has to spin, okay? Because assuming it's not skidding, right? What do I know about this point where the wheel touches the ground? If you're in a skid, right, you're sliding across the pavement. If you're not in a skid, what is your tire doing?
Turning?
Spinning.
It's turning. And it's not just that it's turning. What kind of friction do you have if your wheel's not skidding?
Static.
Static friction. which means that there is no velocity difference between the edge of your tire and the road. Okay? Which means that your tire has to have 0 velocity right there. Now that's weird, because if your tire has 0 velocity here and some velocity there, that seems kind of odd, right? Well, it turns out it's actually perfectly normal, because when you're spinning a tire, right? Let me draw this again, right? If I'm spinning a tire and I want this spot to have 0 velocity, and I want this spot to have some velocity v, how fast does the top of your tire have to be going? Come on, take a shot. The bottom's going 0, the middle's going velocity v. How fast is the top of your tire going?
0.
0.
Really?
I took a guess.
You took a guess. That's what I told you to do. Let's think that through. Okay. Which way is the tire rotating?
Clockwise.
Clockwise, right? The tire's rotating this way. Okay. So the down here, if I drew a line on my tire, right? The rotation of my tire would be such that at this point, the let's say this isn't a tire, right? Or it's not on the road. Let's hold it up and spin it around. Okay. If we didn't have this velocity in the middle, right? Then at the bottom, which way would my velocity be? If I just pick up the tire and spin it, right? This way.
It would be towards the left.
Yep, be that way, right? And at the top, it would be the same velocity, but in the opposite direction. Does that make sense?
That's if it's in the air.
That's if it's in the air. Now let's put it on the ground. Let's make it so that this velocity is 0. That velocity is v. What about, so this guy is in, putting it on the ground just makes it so now the whole tire is moving forward. Okay? Rolling, what tires do, any kind of rolling motion, it happens to be 2 different types of motion layered on top of each other. It's the rotation and the translation on top of each other. So it turns out this guy on the top here has twice as much speed, 2v. If that's 0 and that's v, this guy has 2v. Okay, why am I talking about this? Well, what that means is if I want to rotate, if I'm a tire and I want to roll along with my car, my angular velocity has to be such that it's the velocity of my car divided by the radius of my wheel. And the same is true for acceleration. I chose this formula here because my r, right, the radius of my circle, is, and my angular acceleration, which if I'm rolling forward is into the page, right? So my r cross a would have to give me, wait a minute, did I just do that wrong? Now I've puzzled myself. Did I write all these wrong? R, okay, spinning this way, it's definitely into the page. I might have written those cross products backwards, but this is fine. So these two are perpendicular to each other, which means I can just write out this thing with the magnitudes. I know the acceleration of the center of my wheel, so I can figure out the angular acceleration of my wheel.
Didn't you say that the only way that it would be like a multiplication, it would be if it was parallel or something?
If they're perpendicular. If they're parallel, the cross product is 0. So let's think about that. Which way is my R? Well, there's R, right? My angular acceleration, because the tire's spinning this way, clockwise, is into the page, right? So that's perpendicular to R. So I can just use the magnitudes. Does that make sense?
What doesn't make sense is when you said the angular acceleration. 'Cause
Okay.
remember we said that earlier that the acceleration was pointed towards the center, but that was just for just regular centripetal acceleration. This is
Right.
this is angular acceleration, so it's I'm
So the
assuming it's
angular
different.
acceleration is not pointed towards the center. Okay, so let's put it this way. The angular velocity is this way. Does everybody like that? The angular velocity is clockwise. So I can get the direction by doing the right hand rule. I roll my fingers in the direction and I point into the page. Does everybody like that?
Yes.
Okay. So if that's true, right, the angular acceleration is just the time derivative of angular velocity. Well, angular velocity is into the page, right? And it's getting bigger. So its derivative is positive. So it's also into the page, right? Same direction. Does that make sense? So our angular acceleration is pointed into the page here. Okay. Yes, no, maybe. We like that. We don't like that.
Could you like
Yes.
draw an example of maybe of two vectors where if you rolled your fingers, it wouldn't point into the page? Like just something different?
I can't draw that on a page because if both the vectors are on a page, they all have to point out of the page.
I see.
So this is the frustrating thing about this. You need to be able to see this in 3D. and we're reduced to this this kind of garbage way of doing it. So let me take another example. How can I do this? Okay, here's one more example. Take your fingers on your right hand, the 3 fingers on your right hand, put them like this, right? Stick your forefinger out, your first finger out, your pointer out, your middle finger sideways, your thumb up. Okay? The cross product between your pointer finger vector and your middle finger vector is your thumb vector. Does that help at all? Does that give you an idea of sort of the 3D nature here? And you can rotate that any way you want, right? The relative position of the vectors doesn't change. So your pointer finger vector is A, your middle finger vector is B, your thumb vector is C. So A cross B equals C. And you can do that any angle you want, right? I tell you what, I do not care for trying to teach this through a camera.
Dr. Nelson, would
Yep.
it, in this example you're giving with the hand, would it rotate around your thumb, or would it, like, how is that the angular velocity?
Yes. So in this case, if we're talking about rotation, right? If we're talking about the rotation between things, right? Okay, let's go back here. Okay, I think I've got these backwards. So let me fix this. This is omega cross r. This is theta cross r. And this one, oh, I got to write on the paper. This one is angular acceleration cross r. Okay, so we figured out, remember, that we need V to be pointed this way. V is our thumb, right? R is the radius vector. So there's R pointed up, right? Going back to our example with the clock. So that means that omega has to be pointed towards the camera. Does that make sense? So I apologize. I wrote these backwards.
Can you repeat that again, please?
Okay, so we know R and we know V, right? And here is our formula, right? V is equal to omega cross R, okay? So we need our thumb, the product of the cross products, to be pointed in the direction of V. So put V, your thumb in the direction of V, okay? We need the middle finger to be pointed in the direction of R, okay? So R is this way. So I need to figure out how to rotate my hand in such a way that V and R, wait a minute, now I've got it wrong again. What am I doing here? Oh goodness, I'm all wrapped around the axle here. All right,
It's all backwards, huh?
let's try this again. Circle, we've got a clock. We've got a clock hand. There's our radius vector. There's our velocity vector, okay? It is rotating around this way, which means, there's my problem. It's rotating this way, right-hand rule. That means omega is pointed into the page. So I was right the first time. Velocity vector is r cross omega, okay? We can figure this out by saying, okay, so V is going to be our thumb, and R is going to be our pointer, which means omega is going to be our middle finger, okay? So put my thumb in the direction of V. I put my pointer finger in the direction of R. That means my middle finger. Wait a minute, I just did this wrong again. We may have to come back to this. Thumb, pointer, middle finger. Okay. R, omega. Yeah, no. I'm wrong again. One more time. One more time. There's R. There's V. V is omega cross R. So V is our thumb. Omega R is our middle finger, which means omega will be pointer. Okay, so thumb, middle finger has to be pointed that way. Pointed. Let's see. I got to figure out how to do this. So thumb, middle. Now I got to try to point my hand this way. But you see that? There we go. I can't bend my hand like that. My thumb is pointed to the right. My middle finger is pointed straight ahead, which means my pointer finger has to be pointed down into the page. There we go. Okay. So that means our position vector is, omega or theta cross R. and our acceleration vector is our angular acceleration across r. Okay, those are only important if we're talking about things that aren't perpendicular, which we will get to next time. Okay? For today, we're just going to work this problem as if the acceleration vector, that all three of these are perpendicular. Okay? In other words, we're only accelerating the edge of the wheel tangentially. We're making it spin faster as we accelerate forward. Okay? So the acceleration of the wheel has to be equal to the radius times the angular acceleration. Okay. Have I completely lost everybody? A little bit? All right. Well, let's finish this problem, and then we'll sort of take stock and see if we can come back and regroup a little bit here. Okay. So our angular acceleration of this wheel has to be 10 radians per second squared. If I want to know the angular velocity, all I have to do is integrate that. That's just the integral of my angular acceleration over time, which means it's just my angular acceleration times time plus my initial angular acceleration. And if I want my angle, I just integrate that. So I get 1/2 angular acceleration times time squared plus angular velocity, initial angular velocity times time plus my initial angle. This should look very familiar, except for now we have Greek letters in these spots instead of Latin letters. And because this is just kinematics. So the angular velocity of the wheel, well, I had no initial angular velocity because I was at rest. So after 100 seconds, right, my angular velocity is 1,000 radians per second. And my angle after 100 seconds is just 1/2 times 10 times 100 squared. I have no initial angular velocity and no initial angle. So I've got, let's see, that's 10,000. I've got 50,000. Okay, because you know, people do interesting things in the United States and actually throughout the rest of the world, we don't measure things on our cars in radians per second. What do we measure them in?
Revolutions per minute.
Yep, revolutions per minute. Why? I don't know. Because people like that, I guess. But 100 radians per, or 1,000 radians per second, how would I change that into revolutions per minute? Well, I just have to do some unit conversion, right? So I've got 1,000 radians per second. How do I get rid of the radians and turn them into revolutions?
Divide by 2 pi.
So there are 2 pi in one revolution. There are 2 pi radians. Okay. And how do I go from seconds to minutes?
Multiply by 6.
Yep, there are 60 seconds in 1 minute. Okay. Now, a quick rule of thumb, 2 pi is pretty close to 6. So a quick rule of thumb is that going from radians per second to revolutions per minute, you multiply by 10. Okay. So that's saying that this tire is spinning at 10,000 revolutions per minute, which if you know anything about cars is really, really, really fast, right? But then again, you have been accelerating at 4 meters per second squared for 100 seconds. So you should expect to be going really fast. Okay. Whew. That
Dr.
got
Nelson,
that got a little out of hand. How are we doing?
Good.
I think I know why we use revolutions per minute.
What
It's
is that?
It's because this nation was founded on revolution.
There you go. We're all revolutionaries here. All right. So let's try to do a quick recap, and then I think we're going to be done for today, and I'll try to figure out how to not screw this up next time. So, quick recap. We have two sets of analogous variables. We have one for distance, and we have ones for angle. Okay. For distance, we talk about position, velocity, and acceleration. For angle, we talk about angle, angular velocity, and angular acceleration. Okay. These things have units of meters, meters per second squared. These things have units of radians, radians per second squared. And as long as we don't worry about direction, we can figure out direction using the right-hand rule, okay? If you know which way it's spinning, curl your fingers in that way and your thumb points in the direction of rotation, okay? The transition between angle and distance is just a factor of r, the radius, okay? So if I know how fast it's going in velocity, I divide by the radius and I know its angular velocity. If I know how far it's gone, how far an object has moved along a circle, I can divide by the radius and get the angle. If I know the acceleration along a circle, right? So the tangential acceleration, I divide by radius and I can get the angular acceleration. Okay? That's the key takeaway here, is that what I want you to understand here is that you can relate you can do exactly the same things we've been doing with these distance variables with these angle variables. Okay? And the angle variables are what you want to use if we're talking about a rotation of a solid object, not the rotation of an object about a point, right? Like a bucket swinging around a rope. But if we wanted to actually talk about an object spinning about itself, right? If we want to actually make the pen spin, we want to talk about angle, not distance. Okay, questions? All right, let's do this. Let's call that class for today. So we're going a little shorter than we normally do. But I need to come back and think about how I'm going to try to do this better next time, because obviously today has not been my finest performance. So let's stop for today. We'll come back to it next time. Next time's class, Friday's class may be a little bit longer than normal. I won't keep you for the full, I won't keep you for 7 hours or anything like that. But, maybe an extra 15 minutes or so. And I'll try to come up with a better way to explain cross products. Sound good?
Yep.
Sounds good.
Okay.
Don't forget, everybody, I'm holding office hours tomorrow from 11 a.m. to from 11 to 1 tomorrow. So I'll try and be there tomorrow. I'm going to I have some books that I can recommend to you guys, especially when dealing with cross products, because that's honestly going to be the hardest part about this unit, is learning about cross products and learning about, we haven't even covered moment, sub inertia, which that will probably be next week. But as of right now, brush up on cross products, brush up on your vector calc. That will be the part that is the most useful to understanding this part.
Thank you.
All right. So we'll come back Friday and we'll take another run at this thing. All right. I'm going to stop the recording and we'll call that a class.